Bam! Mr. Tarot. In this lesson, we're going to look at an example, the algebraic process of finding the cross product between two vectors. It's going to give us a third vector. Different than what we got when we took the dot product between two vectors. That's just a scalar multiple. Then we're going to look at the geometric relationship between our original vector u and vector v and our vector cross product, our third vector. How is that new vector related to the two original vectors that you ran through the cross product process? We're going to check that geometric relationship with a dot product, look at a graphical diagram of that relationship, and then finish with the properties of a cross product. So let's go ahead and get going. Our vector cross product, given vector u and vector v in component form, we have the vector cross product. A lot of books or a lot of teachers would just to say the cross product. It's nice to start with the word vector, though, to remind you that your answer is a vector. Again, not a scalar multiple like it was with the dot product. Of vector u and vector v is another vector given by, so this is a vector, u sub 2 times v sub 3 minus u sub 3 times v sub 2. That's going to give your coefficient for vector I, your unit vector going in the direction of the x-axis, minus, so our signs are alternating, plus, minus, plus, minus u sub 3 times v sub 1 plus u sub 1 v sub 3 times vector j, your unit vector going in the direction of the y-axis, plus u sub 1 v sub 2 minus u sub 2 v sub 1 times vector k, the unit vector going along in the direction of the z-axis. Okay, that is a long formula. Probably going to think that that's really hard to remember and recall every time you need this formula. It would be, except really all you're looking at here is three determinants of 2 by 2 matrices. You want an easy way to come up with this formula for the cross product of two vectors? Well, you're just going to do this. You're going to set up a matrix notation. Identify your first row as your component vectors of I, j, and k. And then in the second row, you're going to put the components along the x, y, and z axis for vector u. And your book may be using something like, I don't know, a times vector I plus b times vector j plus c times vector k. The textbook I'm working from does a subscripts of u sub 1, u sub 2, u sub 3, which is nice because it tells you that you're talking about the components of vector u and the components of vector v. Now take your x, y, and z components for vector v. And then start working through the determinant process. You know, how do you take the determinant of a 3 by 3 matrix? And there's a few patterns to work through, but what we're going to be taking a look at is going, okay, let's set up this coefficient for vector I. So we're going to cross out the column and the row that vector I is in, and we're going to take the determinant of vector u sub 2, v sub 2, u sub 3, v sub 3. Now, so we're going to do, with a 2 by 2 matrix of u sub 2, v sub 2, u sub 3, v sub 3. The determinant of that 2 by 2 matrix is going to be our coefficient of vector I minus, we're just going to keep going here, the determinant of okay, now let's look at vector j. So we're going to come through here and we're going to cross out the row and the column that vector j is, and of course it's going to be kind of an ugly mess by the time I'm done. I'm just trying to highlight with colors the different patterns here. U sub 1, v sub 1, u sub 3, v sub 3. And let's see here, how about red? Plus the determinant. And what we're going to do, I'm just showing you how this formula, how you can develop this formula. We're going to cross out the row and column where our component k is in. That's going to leave us with, well, it seems like nothing's left, but we're red. U sub 1, v sub 1, u sub 2, v sub 2. And the determinant of that 2 by 2 matrix is going to be our coefficient of vector k. Now hopefully you remember this, but if not, I'm going to remind you. If you want to take the determinant of a 2 by 2 matrix, you multiply down to the right and get, well, you're multiplying, you get a product. So our u sub 2, v sub 3. And then as you multiply from the bottom left-hand corner up, you get another product, but you subtract. So minus u sub 2, u sub 3. Try that again. V sub 2, u sub 3. If I could write. Okay, so do you see here? It's the same coefficient, or scalar multiple for vector I, component vector I. And if you just understand that if you set up a 3 by 3 matrix, again with that first row being your components of I, j, and k, put the components of vector u, one of your vectors, the components of the other vector in the third row, and do determinants of 2 by 2 matrices, as long as you can set that up, you don't have to necessarily remember this big, long, ugly formula. Now, in this example I'm about to do for you, I am going to write out the process of doing this cross product in this expanded sum of component vectors. But of course, you can write this as the cross product of u and v and just write these determinants as your components of your x-axis, y-axis, and z-axis is this. Well, if you remember your signs. Now I am unfortunately prone to way too many sign errors and silly errors than I'd like to admit, and I do find it easier to remember to have the plus, minus, plus, and write out those determinants in that expanded I, j, k component form, the sum of those component vectors, whereas if I try and go right to the component or the column format for your component vectors, I'll tend to forget that set of negative parentheses for the second row, where I won't when I expand it out like this. That's why I prefer this notation as opposed to writing, jumping right into that column format of a vector. So let's get to our first example right now. So we're going to find the cross product of vector u, which has the components of -3, 1, and 2, and vector v, which has the components of 5, -2, and 1. Okay, so we're going to start off by not writing that big old ugly formula out, but we're simply writing a 3 by 3 matrix. And we have our first row of vector I, j, and vector k. We're going to write out vector u, and I'm pausing because there's something I need to talk about with the properties of the cross product, but I think I'm going to do that after I'm done with this example. Technically, this set of directions is missing something. Find the cross product of is too vague of a statement actually for this problem, but we're going to roll with it because it'll be a good teaching moment as soon as I find some white chalk. Okay, as long as you remember how to find the determinant of a 2 by 2 matrix, you are good. So we're going to say that this is equal to the determinant. I'm not going to scribble all over my matrix again here, but again, crossing out or thinking about crossing out the column and row that has vector I, we're going to have the determinant of the 2 by 2 matrix, 1, -2, going in columns, 2 and 1. Now minus, plus, minus, plus. Alternate those signs. The determinant of the 2 by 2 matrix you get by crossing out the row and column that has the j component vector, -3, 5. Going in a column, 2, 1. Now plus the determinant. Take out the row and column that has the k component, -3, 5. 1, -2. And I need to point out here that since I have my vector u in my second row and vector v in my third row, this is going to be equal to the cross product of vector u and v. Now, determinant of a 2 by 2 matrix, multiply down, get a product, multiply up, and you subtract. So it's 1 times 1 is 1 minus -2 times 2. That's going to give you your coefficient of I, minus parentheses down, negative 3 times 1 is negative 3, minus 5 times 2, which is 10. And that's going to be your coefficient of vector j plus your determinant now of this 2 by 2 matrix down to the right, negative 3 times negative 2 is 6, minus 5 times 1, which is 5. That's going to give us that u, the cross product of vector u and vector v, is equal to 1 minus negative 4, which of course we understand is going to be 5. We got negative 3 and negative 10 is negative 13, minus, we're looking at a plus 13 vector j, 6 minus 5, so plus k. So you may say this in component form is 5, 13, 1. And that is our vector cross product. And just to make sure, because I'm talking and writing at the same time, yes, that is the correct answer. Now, let's go ahead and write this up here. We found that if vector u is our negative 3, 1, 2, vector v is 5, negative 2, 1, our cross product is 5, 13, and 1. And it's just a vector. What is it? I mean, is it anything special in relation to these two original vectors of u and v? Let's get this out of the way and check this relationship with the dot product. Now, because my vectors are in component form, we're going to be doing using the algebraic definition of a dot product, which is u sub 1, v sub 1 plus u sub 2, v sub 2 plus u sub 3, v sub 3. There's also a geometric definition, which is the dot product between two vectors is the magnitude of vector u times the magnitude of vector v times the cosine of theta, where theta is the angle between vectors u and v. I'm going to keep that up there because I'm trying to remind you, if I'm just assuming you're just starting off with your journey of vectors, I'm going to remind you of those two formulas, and something special is about to happen. So in a different color like orange, let's find the dot product between u and v and vector u. So we're going to do the dot product between 5, 13, and 1, and negative 3, 1, and 2. Well, we have 5 times negative 3 is negative 15, plus 13 times 1, almost misspoke there, is 13, and 1 times 2 is 2. Well, the scalar multiple that we get out of the dot product is, well, 0. What does it mean when your dot product is equal to 0? Hopefully remember that from your previous assignment. It just seems like a number that's coming out of this algebraic definition of a dot product, but if you look at the geometric definition, yeah, the only way that you're going to get the product, the magnitude of u times the magnitude of v times the cosine of theta, the cosine of theta, the cosine of pi over 2 or 90 degrees is equal to 0. So if your dot product is equal to 0, then your vectors are orthogonal, or you may say that they're perpendicular. So there's a special relationship between our cross product that we got and vector u. Well, let's see if the same thing happens with vector v. Five times 5 is 25. We have 13 times negative 2, so we're going to add that product. 13 times negative 2 is negative 26, and then 1 times 1 is 1. And lo and behold, that comes out to 0 again. So we've got a couple of properties out of the way already. One, when you take the cross product of two vectors, you get a third vector, which is orthogonal to the two original vectors. Now, if you have two vectors, and if they're sharing, because we're talking about theta being an angle between these two vectors, so if you position them so they have the same initial point, and these two vectors are going off in different directions, well, then these two vectors, again, if they're sharing that initial point, are in the same plane. So you have a common initial point between these two vectors, otherwise you can't talk about an angle between the two vectors. And we have some terminal points, so those 3 points are defining a plane. That's a two-dimensional, a plane is two-dimensional, but your cross product here in white, except this is already in white. Let's see here. How about this? There's U. There's V. And now here comes our white cross product, which is going to be, as we just showed, with the dot product being 0, orthogonal to the two original vectors. So this idea of two vectors in the same plane getting a cross product which is orthogonal to each of the two original ones means that, well, we're talking about 3 space here. So while your dot product, is defined by any type of dimension of space, we're only working with 2-dimension and 3-dimension. Your cross product is only defined, at least again in terms of what we're doing in our high school math class, or maybe, I'm not sure what you in college and whatever maybe you're studying, but I'm only talking about working in 2 space and 3 space. So your cross product is defined in 3 space, whereas your dot product is defined in both 2 and 3 space. And apparently there's spaces that go above 3 dimensions, but yeah, I don't know anything about those. So cross product defined in 3 space, where our dot product is defined in both 2 and in 3 space. Kind of cool. Now, what happens, remember when I said that the language of this was a little bit vague? I'm going to just show you this example. I'm not going to talk through it again because it's just the same process of finding the cross product. But what were to happen if you find this cross product in the other direction? Is cross product sort of, commutative, like addition and multiplication is? About to find out. No, 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 no. Well, as you can see, while the cross product of U crossed with V and V crossed with vector U, the answers are very closely related, but they are not the same. You have the same components, but they're all, in this case, negative. But they're these are negative, but these are opposite vectors. The sign of your component along the x, y, and z, each of those components change sign. They just happen in this case be all going from positive to negative. So going back to this diagram where we have vectors, 2 vectors that have some angle between them, the cross product is going to be a 3rd vector which is orthogonal to the 2 given vectors. And if in this particular case we have vector, the vector which is the cross product of vector u crossed with v heading up, well, then in the exact opposite direction we have vector v crossed with vector u, or negative, the opposite of vector u cross vector v. Now I haven't done any proofs in this, it's just an application, just an example, basically worked in 2 different directions. But we actually hit a few of your properties of cross products, so let's just get a summary of all of those up here on the board and finish this lesson. Our properties of vector products, or cross product, whatever your textbook is calling it. Like we just showed with an example, not a proof, but this is always true. Vector u crossed with vector v is the opposite of vector v crossed with vector u. Vector u, the cross product of vector u and the sum of vector v plus vector w can be found by doing the cross product of vector u with v plus the cross product of vector u with vector w. We have here the cross product of vector u and v dotted with the dot product of that cross product dotted with vector u is equal to 0, or vector v which is equal to 0. We just talked about that again with examples, that your cross product is going to be orthogonal. That's why the dot product is 0 to each of your 2 original vectors. The cross product between 2 vectors is equal to 0 if and only if your two vectors are collinear. Your textbook may have a proof of that property in there. I'll probably in the future be doing a proof of that property as well, even though I'm a little, not my strong point, proofs. Vector u crossed with vector u is also equal to 0 because, well, it's the same vector, so those will be collinear as well. The scalar product, the scalar multiple, or lambda, times vector u crossed with vector v is the same as simply, if you helps your particular problem, take the cross product of vector u and vector v, and then when you found that third orthogonal vector, your cross product vector, you can then multiply that by lambda. And the magnitude of your cross product, the length of that third vector, which is orthogonal to your two original vectors you found the cross product of, is equal to the magnitude of vector u times the magnitude of vector v times the sine of theta, where theta is the angle between vector u and v. And it'll be very common in our upcoming problems. We'll be talking about it repeatedly through the rest of the chapter, where if you have a couple of vectors within a plane, when you find that cross product, you're going to find a vector which is orthogonal or perpendicular to the plane, which then contains those two vectors. And you can use that normal vector, the normal vector to the plane, to find the angle at which two planes intersect. If you have a couple of vectors in one plane and a couple of vectors in another plane, and you do the cross product of each of those two pairs, and you have these two normals, you can then find the angle between those two vectors, which is going to help you find the angle between those two planes. So this idea of the magnitude of the cross product vector, you can find it without necessarily using this formula, but it's nice to have in your back pocket, and it will come in applications later on in this chapter. I'm Mr. True. Bam! Go to your homework.